Hi everybody, welcome to video 7.1.1. Today we're going to start talking about galvanic cells in our electrochemistry. So we're going to start off with an example of an electrochemical cell here. So this exact one is called the Daniell cell, and this was first designed in 1836 by the British chemist John Frederick Daniell, which is why it's named the Daniell cell. This is a type of galvanic cell, and right now we're going to analyze how this works. So in this example we have a copper electrode placed in 1 molar copper nitrate solution. So notice we have a pure copper electrode, so solid copper, and the copper nitrate. We don't really care about the nitrate right now. All we care about is the copper, because eventually our copper and our copper 2+, that's where the reaction is going to happen. And we also have a zinc electrode, solid zinc, and that's placed inside a separate 1 molar zinc nitrate solution. The electrodes are connected with a wire, which you'll see across the top, and then we have a salt bridge in the middle. That salt bridge has potassium nitrate in it. That's placed between our two solutions. So this is porous, and it's got a bunch of potassium nitrate just kind of inside this. And the ions inside the potassium nitrate can flow freely through these. Now, the purpose of the salt bridge will be explored in just a few minutes, so we'll just suffice it to say it's there for now. So let's take a look at what's happening here. Before we get started, we need to kind of remind ourselves what reduction and oxidation are, because electrochemistry is all about redox. So if we remember, we had oil, RIG as our acronym. Oxidation involves loss of electrons. Reduction involves gain of electrons. So if we're losing electrons, we're becoming more positive when we're oxidized, and when we're reduced, we're gaining electrons, right? And so we're going to get more reduced or more negatively charged. So let's take a look at what's happening on this side with the zinc. So our solid zinc, solid, so that's our electrode right there, the solid zinc, that is going to turn into zinc ions, zinc 2+, plus 2 electrons. This is producing electrons. So this is going to be the oxidation side. So this is the oxidation side of the cell. And we can tell because we're losing electrons here. Now, where do these electrons go? So the key is that these electrons now are going to move through this wire over here. So our electrons are going to be produced on the zinc side, and they're going to be moved along the wire, right, from left to right. Now what's going to happen at the copper side? Well, those electrons are going to enter into this solution, and they are going to bind, they're going to react with these copper ions. So our reaction becomes copper 2+ plus 2 electrons that came over on the wire is going to form solid copper, right? And so since we are gaining electrons here, reduction involves gain, this is the reduction side of the cell. Now, oxidation, the oxidation side of the cell, when we're talking about galvanic cells, has a special name. So the oxidation side, this is the anode, and the reduction side is the cathode. So the anode is oxidation, reduction happens at the cathode. Again, oxidation happens at the anode, reduction happens at the cathode. Now, after some time, the mass of the zinc electrode, this bar, decreases while the mass of the copper electrode increases. We're going to write the half reactions that explain what's happening and why. And so whoever's doing this reaction has noticed that this zinc is getting smaller and smaller. So if we have our mass of zinc electrode, and that decreases. So what's happening there? So we're going to copy our reaction. Zinc, we already looked at that. Zinc solid is turning into zinc ions, zinc 2+ ions, plus 2 electrons. And in this case, we can say that zinc is being oxidized. So zinc is oxidized. So what is happening there with that zinc? Well, it's turning from solid zinc into zinc ions, and it's going into solution. So you're almost dissolving the zinc. You can almost think of it that way. But the zinc ions come off, the electrons, they're separate along the wire, and the zinc ions end up in our solution. So we end up having less solid zinc, and this electrode shrinks in size. Now we also notice that when the electrons are transferred to the copper side of the cell, the mass of the copper increases. So what's happening over there? So mass of copper electrode increases. So we know from up above we had our copper 2+, ions in our solution plus 2 electrons from our wire, right, that were transferred from the zinc, gives us solid copper. And that solid copper deposits itself all along the outside of this cathode here. And so you'll end up getting kind of a bulgy look under the water right there of solid copper. And our copper is reduced. Now, if we look overall at the overall reaction here, we can see that we have 2 electrons transferred, right? And so let's go ahead and write ourselves our overall reaction. So overall, zinc solid plus our copper 2 plus, right from here, so zinc solid, copper 2 plus, it's going to yield solid copper plus zinc ions. And our electrons are going to cancel out because those have just been transferred, so they're the same on both sides, so those are going to cancel out there. Now, part B, identify the half cell in which oxidation, the anode, and reduction, the cathode, are occurring. Identify the direction of the flow of electrons in the circuit. So we've already done that, so we can just see above for that. So the zinc electrode, that's our anode, and our copper electrode is our cathode. And when we look, our electrons are flowing from the anode, from the zinc, to the cathode. And that's always going to be true in our galvanic cells. So the electrons are always going to travel from the anode to the cathode. So let's write that down. They travel from anode to cathode. Okay. So let's go ahead and take a look at the next part, part C. Why does the mass of zinc decrease and that of copper increase rather than the other way around? So, turns out that copper has a higher ionization energy than zinc. So because copper has a higher ionization energy than zinc, that means that it's easier for zinc to lose electrons than copper. Copper wants to hold on to them more. So it takes more energy to remove the electrons from copper. And so because of that, that's going to dictate, so those ionization energies, they're going to dictate the direction that these will flow, right? So it's always going to go from zinc to copper when we have zinc and copper because copper has a higher ionization energy than zinc. So copper has a higher ionization energy than zinc. So it is easier for zinc to lose electrons than copper. And again, that's because our copper is going to, it's going to take more energy to remove those electrons from the copper because it has that higher ionization energy. So let's just go ahead and write that as a note to ourselves up top. So the electrons flow from zinc to copper due to copper having a higher ionization energy. And I'm harping on this because if you understand this, if you understand that the electrons are going to flow due to ionization energy, I can give you any 2 metals and you can predict which one's going to be the anode and which one's going to be the cathode. And from that, you can tell me which way the electrons will move and you can write your reduction and your oxidation half reactions with no problem. So in this particular example, zinc, its ionization energy is 29 and copper is 30. So you don't need to have a huge difference there, but you do have to have a difference. If you don't have any difference at all, no electrons will be flowing. Okay, so what is the role of the salt bridge? And what would happen if the salt bridge wasn't present? Well, the salt bridge allows for the migration of ions, and we have to have that because we have to complete the circuit. Because a complete circuit will carry electrical charge. It also keeps the solutions neutral. So if you didn't have a salt bridge, eventually there would be no electrons moving around, and that would be a dead battery. So if we think about it another way, over here in the solution, if we're taking a bunch of zinc ions out of solution, remember, this is zinc nitrate, so there's also nitrates in there. Those are negatively charged. And so if we take out a bunch of our zinc ions, we're going to have a hugely negative solution here. Your electrons are not going to want to flow away, right? They're not going to want to flow out of here. And so your solutions can't be super negative or super, super positive. You can't have just a buildup of them. You have to keep that balance. And so the the ions from the salt bridge can flow freely from one to the other to be able to make sure these solutions stay neutral. So it allows for the migration of ions to complete circuit. And that means it carries electrical charge. It also keeps our solutions neutral. And if there's no salt bridge, you would have no electrons moving. And if you don't have any electrons moving, there's no current there. And no current, dead battery. No electrons moving, and that equals a dead battery. Okay, what would the voltage show if a voltmeter were inserted into the wire? So if you took a voltmeter and you measured the voltage in this wire, what would it show? So let's take a look first at our half reactions to kind of take a look at how we solve for this. So looking first at our oxidation reaction, that's the zinc side, right? So that's going to be our anode right here. So zinc getting oxidized. So oxidation is solid zinc yielding zinc 2 plus ions plus 2 electrons. And then let's look at our reduction. Now our reduction is copper 2 plus 2 electrons, goes to Cu, solid. Okay, so what you actually have is a table of standard reduction values. So here's our table of standard reduction potentials. So we can look up the reduction potential, the voltage, of any half reaction we want. Notice these are all reduction potentials. So if you want an oxidation potential, you got to flip these around and also flip your sign. So let's take a look at how we would do that. So if we look at our oxidation reaction that we had before, our zinc to zinc 2 plus goes to 2 electrons. So that's oxidation. Our reduction is copper 2 plus 2 electrons goes to copper solid. So let's see if we can go ahead and find copper. Okay. So right here at the bottom of this page, and you have this as well, you can look this up. Copper 2 plus 2 electrons goes to copper. That's plus 0.34. So that's our reduction potential. Now, in our reaction, we also have oxidation. So we have zinc. But notice, we're not going from zinc to the zinc ions here. It's the reverse. So we're going to look for the reverse reaction. So zinc 2 plus 2 electrons goes to zinc solid. So let's go ahead and see if we can find our zinc on this page. Okay, so it's right here. So our zinc 2 plus 2 electrons goes to solid zinc. That's negative, right one? Yeah, that's negative 0.76. Now this is negative for the reverse reaction. So for us, we're looking for the oxidation potential. We're going to need to flip the sign here. So when we write this down on our paper, I'm going to keep this close. So our E naught, the standard reduction potential at 25 degrees Celsius, there's that naught sign again, meaning standard state, so 25 Celsius. So our E naught of oxidation is equal to plus 0.76 volts. So remember, we have the reverse reaction here, and so this was negative, it was the reverse. We flipped our reaction because we're looking for oxidation, and this shows you reduction. So you're going to have a positive 0.76 volts. Okay, so let's write ourselves a note for what we did here. We flipped the reaction, so you need to flip the sign as well. Okay, for our reduction half reaction, we looked that up, and so the standard reduction potential at standard state is going to be, let's see, what was that? And we don't need to flip this because this is reduction. Remember, this is the forward reaction that we looked up, is plus 0.34 volts. Okay, so now that we have those, we can go ahead and look at our overall reaction. So overall, put this out of the way, we have our zinc solid plus copper, that shouldn't be there, 2 plus, yields solid copper, plus our zinc ions. And our potential, electrochemical potential for the whole cell at this point now, is these numbers added together. So all you have to do is add these numbers together and you get the voltage for the entire cell. So we end up getting a positive 1.10 volts, and that's for a whole cell. So if you were to stick a voltmeter in that wire, it would read 1.10 volts. Now, because these electrochemical cells occur spontaneously, they have a positive standard cell potential, E naught, which is what we just calculated here, and negative standard free energy. Because remember, when something is spontaneous, it has a negative delta G. Spontaneous electrochemical cells are called galvanic or voltaic cells. So these produce energy, they are spontaneous, they don't require energy input. Okay, so that is the end of video 7.1.1. Thanks!